The floor is yours.
Okay, thanks. So good morning again. I will talk about aerosols, modeling, observations, and the focus will be data assimilation, which is the area that I worked in and am working in. And unfortunately, I don't have any slides on the meteorological data assimilation, since I heard that this was already covered in Dr. Resma talk on the numerical weather prediction and specific challenges. Apologies if I repeat some of the information that you already heard about aerosols, but I wanted to give you some background on the aerosols themselves. So let's go to the slide 2.
Anatoly, can you write your presentation on a full screen?
Can you go to slide 2? Okay.
Wait a second. Yes, please.
Okay, so you see here aerosols being important contribution to atmospheric pollution, being part of the atmospheric smog. Especially harmful are particulate matter with diameter smaller than 2.5 microns, which are called PM 2.5, and they're considered the most critical factor affecting human mortality due to air pollution, according to US EPA. And you see here a picture from New Delhi, which was called by CNN the most polluted city on earth, people running a marathon in conditions such as those. And you can imagine how harmful that can be for anybody participating or not, people just living there. But even in cities like Denver, which is in the plains close to where I live, it's often the smog, including aerosols, is quite common, especially on winter days when there is inversion. At the bottom, there is a figure with annual mean concentration of PM 2.5 over the world. And you see that, for example, US is relatively clean, with except for some areas in yellow, industrial areas in Ohio Valley and also in California, but Europe not so much, and also very high concentrations of PM 2.5 in Middle East due to the dust, and India, China due to atmospheric pollution, anthropogenic pollution, even though the Chinese pollution decreased significantly recently. We can go to the next slide, 3, which in addition to this smog that I talk about, they also impact weather in 2 ways practically. One is radiation impacting, either leading to cooling of the atmosphere. In the case of scattering aerosols like dust, for example, mostly, that causes less radiation coming to the ground and cooling directly, and in somewhat opposite way by scattering, by absorption. The absorption has more complex impact in that less radiation reaches the ground, so it cools down the surface, but on the other hand, aerosols absorb radiation and later re-radiate in longer wavelengths, causing the warming. So that's a radiative effect. And there is this impact on clouds with cloud interactions, aerosols being cloud condensation nuclei, initiating formation of cloud droplets, possibly rain. But if there are too many of those, there are too many cloud condensation nuclei, then a rain can be scattered or evaporate altogether because the droplets are too small. So generally, clouds and aerosols are considered the largest uncertainties in estimates of Earth's energy budgets, because all of this physics interaction, chemical interactions become very complex and difficult to track in measurements and in the model. So next slide, slide 4, which is on origin of aerosols. So aerosols sources are natural, such as mineral, dust, or sea salt. Also biomass burning, which can be either considered natural or human, depending how much human can contribute to wildfires. And anthropogenic, strictly anthropogenic, like industry, agriculture, as human activities. So that's one classification based on the sources, natural, anthropogenic. The other classification can be whether the aerosol particles are primary or they are secondary. Primary being those emitted from the surface, like dust and sea salt, and secondary, those that form in the atmosphere due to chemical reactions or condensation of gases. So altogether, the chemistry of aerosols can be very simple, like in terms of this primary aerosols, or quite complex when it comes into chemical reactions and secondary aerosols. And usually, in terms of modeling, complex chemistry is modeled on the regional scale, and with simple chemistry is driven by physical processes. Mostly people model on the global scale. So let's go to slide 5. So if we were talking about modeling of aerosols, we can imagine these physical processes that I listed here, and minimal chemistry, examples being conversion of CO2 gas to sulfate aerosols, and aging of carbonaceous aerosols when the initially hydrophobic aerosols like soot become hydrophilic over time. And this is a basis for a very popular model that is called Gokart. It comes from NASA. And this model has been very popular. This parameterization has been very popular because it was implemented in many models. One of those is NASA model. ECMWF model is very close to this, and NOAA's model, which practically follows NASA's model. So we can go to slide 6. I will talk about the observations, which is, of course, the first and somewhat crucial step in the data assimilation. So the most common observation on the satellite observation on the global scale is called aerosol optical depths. Aerosol optical depth is an integral measure of extinction of radiation by aerosols throughout the atmospheric column by all the different aerosols, and extinction being both scattering and absorption. Extinction is normally determined by this extinction, characterized by the extinction coefficient, which is a function of the wavelengths, refractive index. This is how much aerosol is the wavelengths, the light is reflected or scattered in the particles by the radius of aerosols, and of course by the aerosol mixing ratio, depth of the layer, and it is summation over multiple layers and species, if you consider this observation. And the important thing is that extinction also varies with humidity, relative humidity, because aerosols that grow in size, some aerosols grow in size and will naturally have higher extinction. And also there is something that needs to be mentioned, is that this extinction is normally determined by radiative transfer models, and there is quite significant uncertainty in terms of how this how the values of extinction they vary quite a bit, quite a lot across the various models, and they are big source of uncertainty. So we can go to slide 7, which is just showing the impact, how aerosols interact with radiation across the spectrum. So it's roughly from 300 to 21 nanometers that this interaction is significant. And as I mentioned, absorption and scattering depend on particle size and surface properties. And in terms of assimilation, there is sensitivity to various aerosols at various wavelengths. So this information can help infer speciation or size distribution of aerosols, because we have we have observation across multiple wavelengths, and we can, because that will vary, it can help us determine what species and size distribution the observation belongs to. So for AOD, important thing is that this is only in cloud-free regions, is only mostly, I should say, during the day, but there are some observations. People are trying to retrieve also AOD during the night through lunar light extinction, but that is more in a research mode than practically available now. And the important thing is to note that aerosol concentrations are normally highest in the boundary layer. However, the total value of AOD determined by the whole column of the atmosphere is actually largely dependent by by aerosols in the mid and upper tropospheric layers. So all this caution needs to be basically we have to be careful when correlating high surface concentrations with AOD. So let's go to slide 8. So there are multiple instruments providing aerosol optical depths, but the most common usage, the most common are the retrievals from MODIS. It's an instrument on 2 instruments, Aqua and Terra. And the Terra was launched in 1999 and is approaching the end of its life now. Aqua was launched in 2004. And the other instrument that was, this were launched by NASA, and and the other one is VIRS, which was launched by NOAA on satellite called Suomi in 2011. There is also another VIR instrument on the newer satellite NOAA 20. So this instruments measure light at multiple wavelengths, but they arrive only practically with AOD at 500 nanometers. And there are various retrievals methods, various retrieval methods that people use. Even at NASA, there are several, Dart Target and MAYAC and Deep Blue, and VIRS also has different method of retrieval, of obtaining this AOD, and they can differ quite significantly. So MODIS, the standard MODIS measurements with Dart Target algorithm is a 10-kilometer resolution. VIRS are obtained at 750, it's not kilometer, it's meter resolution. Apologies for this typo here. Even if you look at this 2 maps, you can see that there is significant difference in the retrieval. That may be because of cloud screening, different procedures, because of different reflection of light gleaned from the deserts, for example. So there is quite, it can be quite different. So slide 9, and it should be ground-based, not space-based. Another measurement of aerosol optical depths. This is from a network, ground-based network that is called Aeronet. So it's a extensive land-based measurement network that provides across the world, as you see, that provides retrievals of AOD at multiple wavelengths with unsurpassed accuracy. And this is the network that has been used for tuning the satellite retrievals. The important thing is that, as you can see, there's broad range of retrievals across UV up to high IR, and that provides basic information on the chemical side, on the size distribution and chemical composition, and this is a very good network for verification. It's not really used in assimilation that much, because compared to satellite, is much less dense, but is very high quality measurement set. Also, recently there's some sites that provide AOD at night. So we can go to slide 10. Next type of observation is the space-based LiDAR. And another type of calypso should be Y. I'm sorry, too many errors. But this is a space-based LiDAR. So it's mounted, is an instrument on a satellite that will provide vertical profiles of aerosols and also their type. So this is a very useful observation, not much assimilated because it comes with about 2-day delay, and it's a very narrow swath, but for verification, it's a very potentially very useful observation. We can go to slide 11, which is shows another type of observation with LiDAR, brown-based LiDAR that can provide the vertical structure of aerosols and also type to some degree. So in Europe, there is EarlyNet LiDAR network, and here in the US, is there are also quite a few sites with LiDARs. And EarlyNet in Europe, particularly, it can be useful during this dust plumes that sometimes arrive from Sahara. So potentially, I'm not sure if it is used, but it could be used for in assimilation to help forecasting. And there is another set of observations in the US covering the whole, quite densely, the whole US, continental US and Canada as well. And that is ground-based stations measuring dry PM 2.5, reporting very quickly also urban sites, suburban sites, rural sites, very suitable for data assimilation and in general for reports on air quality. Very fast reporting within an hour and very dense. And there is another set of observations that are here in the US reporting on species, aerosol species, but these are 24-hour averages and that they can be used for evaluation of the models. Slide 12. So this is on what data assimilation is. So data assimilation basically merges observations with models because models are dependent on the initial conditions, and both applies to meteorological models and aerosol models. And if they were not merged with observation, they will become completely chaotic and detached from reality. So by combining model with observations in some optimal way, we can arrive to something of estimation of a true state. So applications of data assimilations are to forecast and to reanalyze. So forecasting would be that you provide, say, initial conditions for the forecast at the next time step, or reanalysis where you just care about obtaining best information about what the atmospheric state is, and you have it for historical record, for science, for the analysis. So for aerosols and chemical modeling, I think in general, errors arise not only due to the initial condition, which is the case mostly for the meteorological model, very dependent on the initial conditions, but also due to the boundary conditions, primarily because of large uncertainty of emission sources. in chemical models, and also quite significant uncertainties to parameterizations, chemical parameterizations, and there are model errors because of, for example, modern numerics. But especially this dependence on emission sources is significant for chemical models. Assimilation method may also improve estimation of the, not only for the basically assimilation uses a method to improve the initial conditions, but model parameters such as emission sources, for example, for forest fires or for anthropogenic emissions, determine release of pollutants or radionuclides. Also important applications for carbon tracker to estimate fluxes of greenhouse gases. So in general, the estimation of parameters requires time dependency. Such methods as 40VAR and the NKF, ensemble Kalman filter, that I will talk a little bit next. But we will cover mostly the initial conditions in this talk. So slide 13, which is introduction to the 3D-VAR. 3D-VAR is a method that is static. It assumes basically there is this what is called cost function, which expresses how much something that we want to minimize. So the first term is coming from the model error, and the second term is coming from the observation departure from the model, and both are scaled by the errors. Model error, which is here described as this matrix B, and R, that is variance of is the matrix determining the error of the observations. And the other, so X here in this formula is something that we will solve for, try to minimize this function. Is this true state. XB is the background, which is the forecast. Y is the observation. H is called forward operator, which is how is an operator that converts model variable to the observation. So in case of aerosols, for example, that would be operator that calculates aerosol optical depths, converting aerosol concentration to the observation. And there are various assumptions on this. The point really is that this is a static measure, so it doesn't vary. The 3D-VAR doesn't vary on the depending on the state. It's assumed that it's a Klein meteorological quantity, so it would be the same for whether that occurs in a front or whether that occurs during an inversion. It's a static method that is usually the model error is usually determined by something that is called NMC method. So you would determine model error based on the differences in results of the forecasts that are 12 or 24 hours apart, for example. So you would issue a forecast at hour 0Z for 24 hours, and you would issue another forecast at hour 12, at 12Z for 12 hours, and you would take the differences between these two forecasts as a proxy for model error. So in slide 14 is an illustration, and maybe we can go back for a second for slide 13. So this B, the matrix that characterizes model error is often expressed as this as this combination of various wavelengths, error correlation, length scales, BZ being correlation in the vertical, V being the variance, and various horizontal scales, and V being the standard deviation of model error. And so we can go to slide 14, where the scales are shown just for this application. So horizontal leg scales. So these are for various times during the day, obtained for the forecast. Say run for 3 months for a season, and you would calculate for every day the difference between this 12-hour and 24-hour forecast, and you will obtain the estimate of horizontal length scales and vertical length scales, and also variance of the error or standard deviation of the error. And depending, for example, on the time of the day, the vertical scales could differ, can be larger during the day, in the afternoon, depending on the mixing in the boundary layer, and short at night. So these are the scales that would basically determine how the error will be, how the observation will be spread in horizontal, in vertical. Next slide. So this was for the PM, for PM 2.5 for regional model. But if we go to the global model and we look at this, so this was, I should say that it's a previous slide, it was assumed that the scales would normally vary in latitude, would vary zonally, and would not differ significantly in space. But if you look for, and that applies quite well to meteorology, but is very poor approximation for aerosols, because aerosols cannot be assumed to vary zonally, or any chemical species really, almost any chemical species that is chemical, I should say pollutant, because you see that here the error very much depends on the source emissions. So the model error, for example, that is calculated for dust over Sahara would be very different from the model error for dust over almost anywhere in the world. So there is a strong dependency of model errors on the site, on the location. So the approach has to be much more complex than the zonal approach that kind of holds for the regional model. So we can go to slide 16, which is an illustration of the model that is of the assimilation method that is run at ECMWF. So they run this model it's a global model, and they run that is similar to go-kart, different characterization of aerosol properties compared to the standard NASA. The algorithm, the cost functions that I talked previously referred to a single time. Here you can see that is there's a sum or integral over all the of the whole model run over a certain period, and that approach is of course time dependent and situation dependent, and it's much superior method compared to the previous one, but it involves computational cost that is much higher. It involves deriving tangent linear model, which is a kind of linearized version of the model, and another operator that is called adjoint. It's an iterative procedure that also tries to estimate this x in the equation, which is the approximation to the true state, and estimation of the true state. So they assimilate MODIS AOD at 500 nanometers, and also recently I think they assimilate VIRS at 550 nanometers. And there are, because there are 14 or 15 species of aerosols, running the whole minimization procedure for all the species is very computationally expensive, so they take a simplified approach to determine the individual species based on the sum of basically based on the contribution of individual species to the basically they split species based on the a priori ratio to the total value of the aerosols. So this is often used for the model provides boundary conditions for regional models over Europe, and also provides reanalysis. The other model is on slide 17, and model and data assimilation system is at NASA. So parameterization is this go-kart that I talked a little bit ago, and another example is how this value of the estimate of aerosol concentrations is obtained is here. So instead of determining in the first place aerosol concentrations from this cost function, they first obtain the estimate of the AOD using this formula. Delta is called increment, which is change due to the calculated in data assimilation change to the forecast, and this increment is basically difference between the analysis and the forecast. So this is what you add to the forecast to obtain this estimate of the true state. So from the increment to AOD, later through correlation you can obtain the increment to the concentration. So next, finally, I need to hurry up. So this is the model that is currently being developed at NOAA. It's NOAA replaced its spectral model, global model, with a model that is based on the 6 tiles encompassing the sphere. Is a new model after many years, using the former one, and uses also Gokart parametrization. And we can skip the next slide, and we can go to our method of assimilating, which is based on the ensemble approach. In the ensemble approach, we obtain model error by looking at the differences between the members of the ensemble. So how much spread exists determine the model error. And here is a schematic what we use. So we run the model forecast, and then we feed it to the operator, AOD operator. It's combined with local ensemble transform Kalman filter, which will provide the analysis for the members. And there's another path that goes through the what is called control forecast. This goes through another minimization procedure, and finally the ensemble forecasts are recentered on the control analysis, and they form the basis for the ensemble analysis, and the cycle continues like this. So we can go to the next slide, which is an animation of analysis that we run, and basically it's an illustration on our model. You can see the observations coming from MODIS and various analyses. So there is European from ECNWF, there is MERA, and there is our analysis. So they are produce quite similar results in terms of AOD. They don't differ much, and you can see the certain constant features like dust over Sahara, this high values of anthropogenic pollution over China and India. And in general, the AOD over ocean is due to mostly to sea salt, and is actually and also you can see the fires here in Africa, in Central Africa. So that's basically for the illustration of this various analysis. We can go to the next slide. And here you see that despite the fact that the AOD was quite similar, the aerosol profiles for these various domains that I plotted.
No conclusion.
Can you say that again?
There is 1 minute left, please.
Okay, so this is just to point that this is despite having very close AOD, the vertical profiles differ quite a bit between the analysis, various analyses between MERA and CAMSIRA and ours in terms of carbons and dust and sea salt. And finally, this is the evaluation of our reanalysis versus Aeronet. And you can see significant improvement in correlation and in bias. And we remember that we had this assimilation only at 550 nanometers. So this is a scatter plot for 500 nanometers. So where improvement is significant. But when you go to the next slide, where we evaluate angstrom exponent, which compares AOD at different wavelengths and its relation to chemical composition and sizes, this is not as optimistic because there is very little impact of the assimilation at 550 on the chemical and size distribution. So basically we can end on this. So go to slide 27. Thank you.